switching point. So I was searching online regarding why during the switching point the current going through the PMOS and NMOS are equal. Right? So we are applying that equation. I didn't find a pretty satisfying answer to it, but still we can imagine whenever the voltage here goes up, the voltage goes down here, and we are plotting a curve like input, okay, V in, and V out will switch off, and we're defining this as VSP as the same voltage, and ideally this should be 2.5 volts if this is a 5 volts logic. Okay, why the currents are the same? I didn't find a satisfying answer. Someone says it's not okay, so it's not exactly the same. There will be a little difference. It's really confusing. So, but when we are calculating this VSP, the equation we used are the square law equations for NMOS and PMOS, and we put them on both sides on each side of the equation. So we assume that they are equal, right? Remember what we did is we have beta n, right? Beta n. So what is beta n? Kpn W over L. I'm just repeating this, okay? Just make sure you can remember that. So beta n is Kpn width over length. What is Kpn? Kpn is mu n COX. That's the mobility of the electrons. This is oxide layer capacitance, unit capacitance. Okay. And square law equation for the NMOS becomes VGS minus VTHN square, and we put on the right hand side of the equation to the PMOS current, beta P over 2 VSG minus, it's VSG minus VTHP square. So they are equal. And we know that VGS is basically VSP at this moment. And VSG is VDD minus VSG. VSP, sorry. At this moment, the voltage here is VSP, and the voltage here is VDD, so the VSG becomes the difference between VDD and VSP. Right? That's why it's written this way. And then you replace the VGS and VSG, and eventually you are getting an equation like this: VSP equals plus VDD minus VTHP over 1 plus beta n over beta p. So that's a conclusion. So why we need this conclusion? Because we need this one to be 2.5 volts VSP. So in that case, this becomes the only, because these are given, right? These are given. So this becomes the only variable, and then we can calculate this one whenever this is 2.5 volts. And this becomes so I'm not showing the process in the middle because this is really simple algebra, right? So move things around, eventually because this is replaces with 5 volts, this is 0.9 volts, 0.8 volts, but definitely only one variable here, and this is pretty much 1, okay? Not exactly, but very close to 1, just let you guys know. You can find out if you want, but it's very close to 1. Okay? However, in here, looking at here, we assume that PMOS, NMOS, do you think they should have the same COX? The PMOS and NMOS are being put in the same wafer, right? They have to share the same insulation layers and everything, so the COX is the same. I think COX is capacitance between, like this. It's capacitance from here to here. Okay, so here's the dielectric, so GOX, right? GOX. So that's gate oxide layer, but there's a value of the capacitance per unit area, which is COX. Okay, and it's given, right? So the poly layer doesn't matter, it's PMOS or NMOS, it's the same distance, same poly, same material. So it has the same capacitance, unit capacitance. So this is the same. But for KPP, it's gonna be mu P COX by definition. So these are the same. Oh, are they the same? There might be a little difference between these two parameters. But that doesn't affect the final results because we are only looking at these two values. Okay, because we know that this is different. This is different. Mobility of the electrons and holes, they are different. And if these two are slightly different as well, but overall, this parameter is the one we are looking at, right? Doesn't matter if how much difference between these two individually. But eventually we know is this is 100 microamps per V square for KPN, and for KPP is 40 microamps per V square. That's given. That's given by the process in the model file. So in that case, because this need to be 1, so what we know that beta n over beta p should be 1 as well, right? In order to make this to be 1. So which is beta n, if we want a 2.5 volts as a switching point, so beta n should be beta p, there should be the same. So beta n is KPN this is KPP. If we treat this part as a ratio, right, one entity here, because KPN is 3 times larger than KPP, right? If you want to make them equal for the ratio here, which one should be larger? By how many times?
KPP by 3 times.
Yeah, so this should be 3 times larger than this. Does that make sense? Because this guy is 3 times larger than this guy, right? N is 3 times larger than KPP. KPN is 3 times larger than KPP. So if you want to make this equal, WP over LP should be 3 times larger than this one, so they can cancel out, so they are equal. So eventually, WP over LP should be 3 times of WN over LN. Or just larger, okay? Larger. Because this is larger, so this needs to be smaller. And this is smaller, this needs to be larger, okay? So this is larger. So which means if you want to achieve the same strength, I mean, this is another way to understand this. So whenever this guy is driving the following circuit, I'm just modeling everything here as a capacitor, but they are just a RC circuits, digital circuits. You can eventually model it as a capacitor, charging and discharging the following circuit. So whenever it's doing this, you can imagine this point is actually being either put up or put down by these two transistors. So which result in that the strength is called the strength, okay, of the transistor really matters over here. Why is that? If you have a stronger PMOS, it will be put up earlier before the 2.5 volts or after 2.5 volts actually. Oh, before the 2.5 volts. I know it's confusing, but let's make it simple. So if you have a stronger PMOS, you can imagine there are two two men, one on the top, one at the bottom, right? So one is super weak person, and the other one on the top is super strong. They're pulling something up or pulling it down. So if I have a strong man on the top, it's able to pull it down earlier and longer. If you have a stronger man at the bottom, so it's gonna able to keep it at 0 or pull it down to 0 earlier or longer, right? Depending on when this switches. So in that case, so sometimes we are talking about stronger PMOS or stronger NMOS. If you need something to be pulled up earlier or put up to VDD and hold the voltage there to VDD longer, then you just have a stronger PMOS. Otherwise, you just have a stronger NMOS. So what can give you a stronger PMOS or NMOS? What determines the strength?
Change
The ratio.
Yeah.
So here's the ratio, right? Given that it's a certain type of technology we are using, if it's a TSMC 180 or C5, we know that we want to use the minimum length, right? We want to use the minimum length or minimum required length without giving us any DRC errors. So in our C5, it's usually 2 lambda. 2 lambda will be what? 600 nanometers, because 1 lambda is 300 nanometers. Remember why? Because C5 is 500 nanometers as a minimum length, and we want to improve the yield, so we don't want to exactly use the 500, the minimum one. So we increase it a little bit by 100 nanometers. So the minimum we should use is actually 2 lambda for length, and we don't want to modify it, because eventually the current is not determined by the individual length or width, it's determined by the ratio, right? You don't want to increase the dimension too much. So keep the minimum length here. So the only one you are modifying is actually the width. And in that case, a stronger PMOS means a bigger width. A stronger NMOS also means a bigger width. That's it. So increase the width, keep the length at the same, but increase the width will make it stronger device. So in that case, let's see. If I got an inverter and I'm increasing V in, here's a V in this time, here's V out of the inverter. So when V in is 0 volts, we're expecting what? 5, right? And eventually it's gonna do this for you, right? It won't be perfect because it's when the two transistors are actually competing with each other, fighting for currents, right? So it's causing a time delay. This is not perfect. So in that case, if I make a stronger, so for example, switching point here is 2.5 volts. I was able to adjust it. I'm making the PMOS width and length ratio how many times larger than the NMOS to make a 2.5? 3 times larger. So the PMOS, in generally speaking, is weaker, right? So we need to make it 3 times wider in order to achieve the same strength. Why is generally speaking is weaker? Why? Remember, just think about what are in there in the KPP parameter. What's causing that? The whole mobility is lower than the mobility of the electrons. So that's why it's, generally speaking, is weaker, right? So we need a wider PMOS in order to achieve the same strength as the NMOS. So for example, assuming that I was able to design a PMOS which is 3 times wider than the NMOS, and they achieve the same strength and switching at 2.5 exactly. And if I want to switch this one to at 2.7 volts instead, what should I do? So it's now switching at 2.5. When I'm increasing V in, it switches here.
Make PMOS stronger?
Make PMOS stronger, why?
So that it pulls up.
Pulls up longer, right? So whenever you have the V in increasing, so because the inverter is the inverter, so when you increase V in, it's trying to pull this V out down to ground. But because the PMOS is stronger, it's able to hold it for a longer time. Okay, it's still holding it whenever it's still increasing V in until 2.7 volts, it's still holding that at 1. So it's in the stronger PMOS here, stronger PMOS. If I want to switch it at 2.2 volts instead, in the stronger NMOS, because a stronger NMOS will pull this down earlier than 2.5. Okay? And now let's talk about clamping circuit of the diodes. You may learn this in analog as well, but might from a different angle. So first, a diode circuit. So there's a built-in voltage VB, which is 0.7 volts if the silicon usually, and plus minus. If you haven't taken analog yet, which is fine because we already learned that this is the pin junction. And here are minus, right? Here's plus. So this one forms the built-in potential with the plus and minus forms the electric field. It is built-in potential, which is 0.7 volts, because when you forward bias it like this, it requires at least 0.6 or 0.7 volts, depending on the material. But let's say 0.7 volts. You need to be higher than that to overcome or to reverse whatever here, right? Because it's providing electric field in that way, and you are forwarding bias it, it's actually providing an electric field in the opposite way, and it has to overcome this one first in order to conducting current in this direction. So that voltage to inverse it, right? Not reverse it, inverse it is gonna be 0.7 volts. So in order to turn on this diode, like this, that way, this need to be larger than 0.7 volts in order to run current in this direction. Does that make sense? Just keep in mind, you need a certain voltage, like 0.6 or 0.7, in order to turn it on, right? It could be 1 volt, could be anything larger than 1 volt, so you can turn it on. And after it is on, there will be a fixed voltage drop across it, which is exactly the built-in potential, 0.7 volts. So if you probe it, there will be a voltage drop across it. So that's an important property we need to know for the diode. And the applications, it's can be used for protection of diodes. But now let's look at IV curve first. If we have a diode, and I'm telling you that this diode is ideal diode, it's ideal diode, just in perfect world, and there's no built-in potential. Ideally, when people design a diode originally, what do they want? They want to conduct current just in one direction instead of two, right? So in that case, they are thinking about, it should directly, whenever I have a voltage trying to forward bias it, I'm applying to here, I should get a current, and there should be no built-in resistance or capacitance. So ideally, it should be this. Should be a wire. If I use it this way, should be a wire. If I give a negative voltage here, there should be no current. Right? This is 0 volts. Ideally. However, in the real world, it's not working that way. It works this way. It's very similar to the VGS to IDS of the unknowns. And when you reverse bias it, when it reaches a certain negative voltage, it breaks down. So for regular diode, it's going to be broken. For Zener diode, you are actually using the breakdown condition to stabilize the voltage. Have you used the Zener diode for circuits before? You have? Anyone else? So you'll see, you know, for example, here's a black box. It's a power supply unit, and it's providing something, and it's probably larger than what you need. So you put a Zener diode. Zener diode's symbol looks like this. So there's a certain rating of the Zener diode. You can purchase a 2 volts, 1 volt, 0.0, doesn't matter. So for example, it's a 1.2 volts Zener diode, and which means the reverse breakdown voltage will be 1.2 volts. So what that mean? If you look at the Zener diode's curve, first Zener diode is a diode, no doubt. It will also show you this after this 0.7 volts, this threshold voltage, it will start conducting current through it, right? But whenever it's going reversely, at a certain point, it breaks down. This is called VZ. So because you are reversely biasing this guy, and that is why VZ is showing up the negative coordinate, so a negative X value, and because it's negative, this is also reversely biased, so it's actually plus minus VZ. So that voltage, the breakdown voltage, if you look from cathode to anode, this becomes a positive voltage, which is 1.2 volts, as a Zener diode's rating in this case, right? So, but if you plot it over here, it's actually negative 1.2 volts. But since you are looking from the cathode to anode, so you can consider this as a 1.2 volts. So this output will be stabilized at plus 1.2 volts, and you are supplying a stable 1.2 volts for your full-on circuits if it requires the 1.2 volts. It's a really simple. It's not even a regulator. It's just any overshoot of the voltage will be cancelled by the ideally infinite amount of current. Let me know if that makes sense. Why? If you look at the curve, that's a device. That's the device IV curve.
Yeah.
It shows you if you're trying to make this more negative, what's going to happen.
It's just gonna keep. I guess.
So the voltage here is not really changing. Is it changing? If it shows VZ, it's probably plus minus 0.1 volt or so, but it's still stabilized at 1.2 volts. So whenever the negative voltage becomes like this one, right? So this one has a accident. It's giving you a surge like this. It should be 1.2 volts, right? 1.2 volts, but there's a surge. Okay, there's surge, and this one will cancel out that surge by doing what?
Basically, the excess current will get
By running a lot of current through it.
Yeah.
By dumping that current to ground to pull this down to the original 1.2 volts. That's how that works. Isn't that beautiful?
It's cool.
Thank you. I don't want you to
Is
be.
that the same, like, PN junction? Like,
No, good question. So for Zener diode, they have different dopants and different concentrations. That's why it's performing differently as a regular diode. It's more expensive as well. So the regular diode, if you do a reverse biasing, and whenever like this one, right? Whenever it goes beyond that current, that voltage, in a negative way, it breaks down. It's broken. You cannot recover it. You don't have this curve. It's done. Okay.
it just kind of breaks.
It breaks, and usually it shorts. It's like a short circuit internally. So it doesn't do that one directional current conducting anymore. Usually it's a short circuit.
That seems really bad.
It is. It's now you have to replace it. It's not working anymore. Because the diode, we need a diode because we only want a conducting current in one direction. And a lot of times you can see here's a VDD power supply, and we have usually we have a. If you look at your microcontroller schematic, right? So they place a diode here while I'm doing that. Okay, so they do this for the power supply. The power supply.
What's the Zener?
No, actually, there's no. It's not a Zener actually. It's like this. I forgot what kind of circuit is over here. We can look up the schematic. But the thing is, I think that's the diode next to the remember the microcontroller board on the top left corner, there's a little diode over there, right? So that diode is one of these ones. So imagine if whenever this got a surge, right? Got a surge, it's gonna break this and
Dump all the current.
dump the current over here instead of damaging your more expensive circuits.
Okay, so it's like
But-
a fuse.
Yeah, but that's still not a. It's a protection diode. I'll show you the circuit of that typical ESD, electric shock discharge. Oh, electric static discharge. So the ESD protection is a really common thing in the electrical engineering field, right? So you need a ESD protection for a lot of electronics components, including IC chips. So every single IC chip you have in your smartphone, everywhere, digital chips, they require ESD protection diodes. So I'm going to draw that schematic after I introduce the clamping circuit. But now, just let you guys know, by using the regular diodes property like this, you can protect the following circuits, and it's called clamping circuit. This is restricting the voltage in a certain range, so it's not surpassing that certain range to damage the following circuit. For example, the integrated circuit we designed and fabricated with TSMC last year. All these, because every single chip requires the ESD protection with the ESD protection diodes, and these circuits are not. You don't even need to manually design them every time by yourself, because everyone needs it. So they directly placed them into the pads. So when you take the pads from the library and place them into your design, the pads already contain the ESD protection diodes, and you don't even need to. We don't even know what the circuit look like or the layout look like. It's already packaged into that. So because that's required. That is why. So what are the pads? Remember, what are the pads?
Like
The pads are the top metal.
Yeah.
So at C5, you go up to the metal 3 layer, right? On the metal 3 layer, you have a little opening, so you have metal 3 exposed. And for all the circuits, eventually you connect to metal 3, so you can wire bond it to the external pads and either probe it or injecting a signal into that pad. That's how we do it. So the pads in a different technology like TSMC338 will be at a certain metal layer, and the pads itself has all the protection diodes there, because that's the first device the external circuit is gonna face, right? So you want that one to protect all the following circuits in the chip. Now we know the property of the diodes, and next we are looking at the clamping circuit of the diodes. I'm going to give you several examples. Resistor here. V out. V in. So if I increase, if you look at this curve, just X and Y. This is V in. Can you plot V out for me? This is V in. V in changes from a negative voltage to a pretty large positive voltage. Why do I need a resistor here? Yeah, all the diodes requires a resistor to protect it. So it's limiting the current. Because the diodes, they don't have large internal resistance. If you directly short it to the power supply, you can blow it up really quickly, including the LED lights. Will reduce the lifespan for like 10 times or so, or even more. So all the diodes require a protection resistor. Could be several hundred ohms, could be 1K, which is fine. So it's just limiting the current. So I'm give you more space over here. If I start increase V in, and assuming the built-in potential is 0.7 volts, okay, 0.7 volts. So eventually, let's think about that. This one, because I'm directly shorting the two terminals of the diode to the output. So the voltage across the diode, whenever it's forward biased, right? It's forward biased, and there's current going through it, and there's the fixed voltage drop from plus or minus, right? No doubt on that, 0.7 volts. So even you increase this further, like 2 volts, 3 volts, after it reaches 0.7 volts, if you're making this larger, are you getting a larger output?
No.
So where's the voltage goes?
Well, I guess for the current to flow through the diode has to counteract the threshold voltage, and so that's going to decrease it, right?
This is not changing. So after this reaches 0.7 volts, the two terminals, because the built-in potential of the diode, is going to stay at 0.7 volts.
Yeah.
So if you increase this voltage more, like output is still 0.7 volts, where's the voltage go? So we start V in start from 0 volts, right?
Yeah.
0 to 0.3. You agree with that?
Yeah.
Why it's linear?
Because
The threshold.
You haven't hit the threshold yet, so assuming there's no current going through this guy. No current, no voltage drop. There's no current. This is disconnected, so there's no current. No current, no voltage drop. Whatever here, right? It's linear. Until what?
0.7.
What's gonna happen? Flat, right? So where's the voltage go? Hmm?
Does it kind of increase the resistance of the
Yeah, so got more-
diode, and then because you get a wider, you get the wider depletions in it, or is it shrinking it?
No, so this is not changing anymore, right? So not changing, it keeps at 0.7 volts. So what's happening is like running current this way because the power supply has a ground loop, right? It's going this way. If you increase the voltage, and because this is fixed, 0.7 volts not changing, so the only place you can drop the voltage is actually here. So why is this resistor can drop more voltage? That's so intelligent. It knows like when it should drop more voltage.
is it dropping the current?
The current is increasing.
Oh yeah, the current is increasing. Resistance is not changing. The current is increasing, so the voltage is increasing, right? It's I times R. So when you have a more voltage and you got a more current, and this guy times the resistor, you're getting more voltage drop across this guy. But this is still fixed. It's not changing. Make sense? So what about negative voltage here? If you put a negative voltage, like starting from 0, and then you start like a negative 0.3, what's going to happen?
There'd be no voltage.
It's going to be linear. There's no current, right? So if you have negative voltage, you are seeing negative voltage here as well. Make sense? There's no current. It's nothing. You can ignore everything here. It's nothing. It's just same thing. So it can be this, linear.
And this isn't accounting for breakdown, right?
That won't break the diode.
That's right. If it breaks it,
Because won't the voltage then go?
okay. Just for you guys.
I just thought
Yeah, why? When it breaks, it shorts, right? Then no drop.
yeah.
Wire. Another case. Assume this is pluses minus. This is pluses and minus. Because I'm assuming it's a plus minus from top to bottom, right? So if I'm forward biasing this diode, I need a negative voltage. Agree with that?
Yeah.
Okay. And if you flip it, it's basically the same circuit, but going to the negative region. So what's going to happen is when it hits 0.7 but negative, right? It'll be flat. Agree with that? What about this region?
Linear than drop.
Yeah.
Linear, right?
Yeah.
Yeah. and maybe breakdown, right?
Okay.
Another example. And you can see it's called the voltage being clamped at a certain level. This is a clamping circuit, clamping circuit. And another example is two diodes at the same time. V in plus minus, V out plus minus. How do you draw the in out voltage?
So you're going to be clamped on both.
Mm-hmm.
So 0.7.
So this is like a way to limit the output voltage?
Output voltage for what?
Like if you're going from VN to V out,
Mm-hmm.
you're clamping really physically.
Yes, clamping that in a certain range, right?
Yeah.
Yeah, it works that way. So for the IC circuits, ESD protection diodes, it looks like this. Assuming that it's 20 volts, and your IC circuits here is IC cannot take any voltages, or it can only take voltages within that range, 0 to 20 volts range, right? Anything larger than that, including larger than the negative range, for example, negative 25 volts, is also considered too big, right? This is a voltage potential, it's just a different polarity, but it's still considered a large voltage difference, which can potentially break it. So so anything outside of this range, or the absolute value outside of this range, shouldn't be taken. So here's the IC, here's the protection circuit of the diodes, and that's the signal, whatever you are putting into the IC. And why this makes sense? Think about that. So what if I'm getting 21 volts? What's going to happen?
The top.
So 20 volts means what? Agree with that?
Yeah.
20 volts is power supply, 20 volts, right? Okay? If this guy is 21 volts, what's going to happen?
It's going to become forward bias.
It's forward bias because it's larger than 0.7 volts. It's 21 minus 20 is 1 volt. Larger than 1. So what's the drop across this guy? You're saying 1 volt. What's the drop?
0.7.
0.7, right? Fixed. Where's the loss? It's going to be lost here, right? So you need a resistor to consume it. So what's the voltage here, though?
Would be.
Look at it.
Would still be.
Plus minus, plus minus. Remember the toys? Has 2 batteries.
Yeah.
1.5, 1.5. Plus minus, right?
So
It's adding up. Plus minus, two batteries for the toy. What's the voltage here?
2.7.
No. Oh, no, 20, sorry, 20. The 20 volts. 20
Oh,
volts.
yeah, it'd be 20.
It's fixed. It's not changing. It's not going to change. So if this one can only take up to 20 volts, or maybe a little bit larger than 20 volts, like 25 volts or something. I don't know. A 0.7 volts increase is not very significant, but at least if you have a 30 volts surge, eventually will consume all the voltages, will drop it across the resistor and protect it by this diode. Only it's clamping this voltage at 20.7, which is very close to 20 or within the range. Make sense?
Mm-hmm.
And what about this guy though?
That's for if it's negative voltage.
For negative voltage, yeah. So if I have negative 1, for example, what's going to happen?
It's going to forward bias it.
It's going to forward bias it, yes, because 0 is larger than negative 1. So getting a 1 volt for biasing circuit is going to draw current from the ground and go through this resistor and consume it, right? So what's going to happen is it's 0.7 volts drop permanently, okay? And because you know this is 0 volts for sure, and 0 minus 0.7, and this ends up with what? Negative 0.7 volts, and it's being clamped, even though you have like negative 5 volts surge, and we'll keep this voltage at negative 0.7. It's not too bad at all. It's still very close to 0 volts, so you can protect this one from being damaged by that surge. Okay. So that is why all the integrated circuit, the pads, they need this ESC protection diodes in it. And how to design the diode? I mean, for schematics, it's very simple. Just 2 symbols, put them together, right? But for layouts, a lot of considerations and requirements. And that's the IP of TSMC. You won't be able to see it. You can only see the pads, but not the details of the layout inside the pads. But you do need to know that there are ESD diodes in the pads, for sure. Okay, keep that in mind. I think we can just stop here. It's Friday. 2 more minutes. You're not asking for refund, right, or tuition?
No.
Just 2 minutes. $5. Any questions on anything? Okay, cool.
I have a question about the for these cross sections. Do we just assume that these are like?
Oh, they're pure NWELs, right? Just draw the NWELs and all the layers on the top not being used, but just want to draw them. Right, and
Oh, because
that's
they're
it.
in office, right?
Yeah,
Oh, okay.
People don't show up. Yeah, he does this for day after exam.